So as I told you last Friday, so I am going to start the lecture which is about galaxies today. Right. So let me switch off the video for the time being. Right. So I assume that all of you can see the presentation right now. Remember that we have talked about our own solar system, which means the planets, and then we moved into talk about stars and their properties and the evolution, how stars evolve with the time depending on their initial mass. And then we talked about motion of the stars, how stars move, different type of motions, and then we talked about variable stars or double stars. And then the last Friday we talked about exoplanets, which is one of the new emerging areas in astronomy, right? So and that this is what we have discussed up to now. Now, starting from today, I am going to move outside our own galaxy, or we will talk about our own galaxy and then move out from the galaxy to look at this large-scale structure of the universe, right? And this is so, which means we are now little bit, moving towards this the concepts about the cosmology. But before we move into the cosmology, we will learn about galaxies and galaxy clusters, right? And now, as you know, as I mentioned you, so we have discussed about a lot of these different types of the stars, and we have discussed how they evolve with the time. And now we are going to move on to the topics about the galaxies, right? Now, when we talked about galaxies, first thing that we have to do is to talk about our own galaxy, which is Milky Way, right? Now, if you go and look at the night sky, can you see any galaxies? That I mean, anybody can see any type of galaxies on the night sky other than stars? Have you ever thought about this? Can you see any of these galaxies up in the sky? I don't think we can see those from the naked eye, right? But there are huge number of galaxies, right? And so it is only in recent times that we learned the existence of different galaxies within the universe. So it's not so long ago. It's very recently that we got to know that there are other galaxies in the universe, right? Apart from the galaxy that we are living, right? So we will start this discussion with an introduction explaining that discovery of other galaxies, how astronomers discovered these other galaxies, right? So because there is a nice scientific, formulation behind this discovery of other galaxies about measuring distances, which I would like to discuss. And then as the next step, we will learn about the structure of the Milky Way. Like we learned about the stars, now we are going to the next step. So we will take the Milky Way as a whole and we will study the structure of our own Milky Way, right? And also how the stars and interstellar matter. And there is something that we did not discuss up to here that is called dark matter. So all these are spread throughout our galaxy. So what we have discussed up to now is about stars and interstellar matter, right? So we did not discuss anything about dark matter, but in this lesson, we will talk about this dark matter also, because actually the huge amount of matter that we have inside our galaxy is dark matter, which we cannot see, right? And so we will discuss about that as well. Now, if you go outside and observe the night sky, you will get the impression that stars and nebula may all be associated with one another. So what we need to talk is this really true? Which means nebula means actually this is like a collection of stars and interstellar matter. And this is the name that initially astronomers have used for galaxies, some of the galaxies, because they didn't know that there are other galaxies. So rather than using the word galaxy, they had this the word called nebula, right? And if you look at very like old scientific papers about galaxies, this is the word initially that they had before this word like galaxy comes into play. And one thing actually that you can see in the night sky for sure is the Milky Way band at some point of the year. Right? So if you go outside to a really dark place, you can clearly see this band, which is the Milky Way, right? And that indicates that there is a patterns of grouping of stars in the sky, right? So there will be a band of stars with some, clouds, which clouds means like some interstellar matter along that line, which is what we can see as our own Milky Way, right? As you know that we are inside the Milky Way. So because of that, we cannot see the whole picture of Milky Way, right? So if we are inside something, we cannot see the whole image of that, no. So what we are seeing is just one side of our Milky Way. So that's why you just see a band like that on the sky, right? And you can see this band even from the naked eye. Now, if you are in a very, kind of in a dark area outside the city, you can easily see this, right? Now, when Galileo and others observed the Milky Way with telescopes, they found many more faint stars there. Right? Now, when you look from your naked eye, you don't see like large number of stars that you cannot see, like, but what you can see is just a band of stars. But if you look at the same from a telescope, this is what actually Galileo did. They found many more faint stars there, right? And so in early days, the common belief was that the Milky Way group is the universe itself, because this is what you can see, right? And people believe that that is the universe itself. So there is nothing else. So they thought that this band of stars that they see, which is the Milky Way group, so they thought that this is the universe and there is nothing else in the universe, right? That this was the first impression about our Milky Way galaxy. And this is just a picture to show you how the Milky Way band looks like if you go, if you go to a dark area and observe the sky, right? Right. And now when you go for early 1700s, there was a belief or speculation that there may be many more stars beyond the confines of the Milky Way itself, right? So this idea came in around 1700, that there may be other stars that are beyond the Milky Way itself. Now, one of these astronomers called Immanuel Kant was the one who first proposed this theory. So he believed that there may be many more stars that doesn't belong to Milky Way, but beyond the Milky Way, right? And when they had these bigger telescopes, they have identified another spiral-shaped nebula. Remember this word again, you will see that this spiral nebula means the Andromeda galaxy when we talk later. But at that time, they thought that this spiral nebula, which were thought to be possible collections of distant stars, right? So that were comparable to Milky Way. So they have this observed this spiral nebula. Right? So they call this as a nebula at that point, which is another like a group of stars, right? And they thought this looks like our own Milky Way, right? But the question is, nobody knew at that time whether those observations that they made are a different galaxy or they are just a part of our own galaxy, right? Now, then there was a debate called Shapley and K.V.S debate, which they debated about this new nebula, and Shapley argued that these nebula were in our own galaxy. So there are a set of stars that they saw on the sky. So some astronomers thought that they have this set of stars in our own galaxy. And Kurtzy is another astronomer. He had a different idea about that. He argued that these nebula were very distant and they don't belong to our galaxy, right? And this was the debate because nobody was able to figure out whether this new set of new nebula, or this group of stars belongs to our own galaxy or whether it's a different galaxy, right? Now, the problem you have, as you can see, that you have to measure the distances, right? So that is the only way of figuring out whether they belong to our own galaxy or it's a different galaxy. Because if you measure the distance to this new nebula, and if it is a huge distance, then you can decide, okay, maybe this is not belong to our own galaxy, maybe it's a different galaxy. But if the distance is smaller, you can directly decide that, okay, these are not that much far away and they should be in our own galaxy, right? So that is the idea. But the problem is, at this time, around 1920s, there was no way that we could measure the distances to these stars, right? As you know, we had this parallax method, but parallax method works only very nearby stars at that. At those times, we didn't have precise instruments, and also, as you know, when the distance increases, this parallax angle, decreases, and because of that, the measurements that you make will be very, very smaller, right? Which leads to a lot of uncertainties or errors in the distance. So because of that, the parallax angle, doesn't work well for stars that are far away, especially if it's from a different galaxy. It doesn't work at all, right? Right. Now, as a solution, they have found, remember, we talked about these variable stars or double stars in last week. And there was an astronomer, actually, it's a lady astronomer called Henrietta. She actually figured out the method to measure distances to these nebulas, right? Now, this method came as a result of these variable stars, and this is a special category of variable stars called Cepheid variable stars, right? And the property of these stars, Cepheid variable stars, is that they vary their brightness regularly, right, as they pulsate. And their periods of variation will range from 1 to 50 days. And actually this, so if I go into a little bit more into background about the discovery of these relationship for Cepheid variable stars, she has actually done this using a set of stars in large Magellanic Cloud, as far as I remember. So assuming that those set of stars that she has observed in the same distance from Earth, by the way, large Magellanic Cloud is another nearby galaxy for us. And then she looked at the period of those stars and the brightness, right? And when she looked at the brightness, she assumed that all of these stars are kind of at the same distance. So you can directly take only the apparent brightness of the stars, right? Because if all the stars at the same distance, absolute magnitude and the apparent magnitude doesn't change that much, right? Now, I assume that all of you remember what absolute magnitude and what apparent magnitude means, right? So we have discussed about these things probably a month ago, maybe 2 months ago, right? And so what she found is that there is a relationship between the period of these stars, because these variable stars, they pulsate, they increase the brightness and decrease and increase and decrease like that. So you can calculate the time it takes between successive maximum brightnesses. So that's what period means, right? And there is a relationship between this period and the luminosity, right? And this is very famous in astronomy, which we call as a period luminosity relationship. Right here I have mentioned it. So if I ask you what is period luminosity relationship, you probably should be able to even explain it, right? It is that much important in astronomy, and you will see why it is important, because this is the relationship that was very helpful in 1920s to figure out that we have different galaxies. And here is the relationship, and if you plot, you can see that the y-axis is average luminosity and the x-axis is period. And on this top right hand corner, I have shown you the light curve for a typical speed variable. Now the light curve means how the brightness change over the time. You can see the time in days in the x-axis, and the brightness, which is measured in terms of magnitudes, which the units for measuring the magnitude is in the y-axis. And one thing that you can see here is this axis calibrated into the reverse order. It starts from 4.4 and it goes up to 3.4, right? So which means the number is reducing, and that means the brightness increases towards the y-axis, right? Towards the y-axis, right? And if you don't remember it, and make sure that you understand the magnitude scale works in the reverse order, which is very important, right? And you can see that the brightness, the magnitude decreases, and the brightness decreases and then increase and then decrease and increase like that. This is a light curve, how the light changes for a Cepheid variable or a Cepheid star, right? And this is a diagram for one star. Now you can measure the period from this one, right? For example, from 2.5 days, this goes up to 8.5 days. So it will be one period from here to here. The period is around 6 days, right? And you can look at 6 right here, and then you can go to, and once you measure the period, then what you are going to do is you are going to measure the brightness of that. And this one point in this graph will represent its period and the brightness, right? Like that, you can take large number of Cepheid variable stars, and you can draw this light curve for each star. And from each star, you can take the period, which is the x-axis, and then for each star, you can measure the brightness, right? Now, when you look at the brightness, what this particular astronomer did was, she was looking at large Magellanic Cloud and got the number of stars which can be considered as Cepheid variables. And since they are roughly at the same distance, which is the large Magellanic Cloud, and then she decided that, okay, it doesn't matter whether you measure the apparent magnitude or the absolute magnitude for the comparison, right? Because they are at the same distance. And then she could measure the luminosity for each star. And what has happened is, then she plot the period of the star and the luminosity, and now each black dot in this graph represent a period of a particular star and its luminosity. And surprisingly, what she has observed is, when the period of the star increases, the luminosity also increases, right? So there is a relationship between the period and the luminosity. And this is what we call as the period luminosity relationship, right? Now you can straight away, you can see the advantage of this. Once we know this relationship, assume that when the relationship is well established, assume that you observe a new Cepheid variable in somewhere, right? Now, if you can measure the period of that particular Cepheid variable, you can directly go into this particular graph, and then let's say you measure the Cepheid variable, a new Cepheid variable star, which has a period of 10 days. So all you need to do is go into this graph and look at this line right here, and for the 10 days of period, the luminosity should be this much, right? From the y-axis, you can read that value, right? And once you have the luminosity, you can directly calculate the magnitude, right? So we have discussed about those equations, and you can actually use this equation if you need, right? This is the equation, the same equation, magnitude equation that has written based on the luminosities and the magnitudes of the sun, right? So that's why you have L sun here. You can easily derive this equation. Probably you will get one or two of these equations to derive in one of your tutorials, right? And so all you need to do is find the period, find the luminosity from here, and plug that value for this equation, and you have the luminosity of the sun here, which you should already know. And this 4.77 is the absolute magnitude of our own sun, if you remember that, right? We have calculated this before, and you just plug the values, and you can find the magnitude of absolute magnitude of that particular star, right? And once you know the absolute magnitude in this way, and once you know the apparent magnitude, you can use this distance modulus, or the equation that you can find the distance, right? That is this equation right here. So once you can calculate the absolute magnitude from the period luminosity relationship, and then you can directly find the apparent magnitude, which is the visible magnitude of that particular star, and this will give you the distance to that particular star, right? In this way, you can calculate distances to other galaxies, right? That is the advantage, right? So I have very briefly explained here how to use the Cepheid to measure distances. A, which is this one, you just go outside and find the Cepheid variable star and measure its period, right? And then you use the period luminosity relationship to calculate the star's luminosity. And this is what I have mentioned. This is a graph of period luminosity relationship. You look at the period, and then you try to find the luminosity. So that's what she has done, right? And then measure the star's apparent brightness. Then you measure the apparent brightness. So once you know the luminosity, you can relate that to absolute magnitude. And then once you know the apparent brightness, you can relate that to apparent magnitude. So when you know the apparent magnitude and the absolute magnitude, you can calculate the distance as the last step, right? Now this is the method that astronomers have discovered to check these distances to the stars that are outside the Milky Way. So at that time, actually check whether these stars belongs to our own Milky Way, or whether they are outside the Milky Way, right? Now, so I have explained it a little bit more here, because this relationship is very important in astronomy. Knowing the period luminosity relationship, it is possible to use Cepheids to measure the distances in astronomy. So Cepheids means Cepheid variable stars, right? And so the method, the way that you use it is, suppose one wishes to measure the distance to the Andromeda galaxy. Think that you are going to measure the distance to the Andromeda galaxy, which is the nearest giant elliptical, not elliptical actually, nearest giant galaxy that we have. So first thing that we have to do is, we have to identify some Cepheid stars in this nebula or the galaxy, right? And these Cepheids can be identified by their periods of variation. So you just observe the sky and look for some set of stars in that direction where you have the Andromeda galaxy and find this different set of variable stars which has periods around 1 to 50 days, right? So that is what you have to do as an observational astronomer, right? And once you find those periods, you can see that this is not an easy task, right? You have to, continuously observe the sky at night for maybe 1 to 50 days. And then the period luminosity relationship will give you the estimate of the luminosity or the absolute magnitude of each star. And then the average apparent magnitude of each sepid can be also measured. So that is straightforward. And once you know the absolute magnitude and the apparent magnitude, this equation right here can tell you the distance, right? So this is the method that they have used. And this is what actually I have to tell you, or I want to emphasize you that how astronomers discover new things, right? So they don't just come accidentally. They had a problem whether they to decide whether they are looking at a different galaxy or whether these things that they are observing are in the same galaxy. So what they have done was look at the absolute magnitude and look at the period. What they have done is actually discover this period luminosity relationship, and then once they have the relationship, they use it to find the distance. Right now, this is what you have to do as scientists, right? The whole idea of practicing or learning all these things to grab this idea about finding something that you never knew or finding solution to problem. For solution to an existing problem, right? Right. Now we know the method. Now let's look at how actually they have used it to solve that debate that we talked, right? Because some people thought that the set of stars of the nebula that they are looking at maybe in our own galaxy, or some people thought that it is outside our galaxy, right? The only way to decide this is to measure the distance. Now, once this period luminosity relationship is established, Edwin Hubble took this challenge to resolve this debate, right? And the Hubble is famous for finding this expansion of the universe, but here what Edwin Hubble has done at this particular point is trying to resolve this debate by measuring the distance to the Andromeda Nebula, right? And actually, you will see that what they were debating about is that they were actually observing the Andromeda Nebula at that time. Now we call it as the Andromeda Galaxy, but they couldn't figure it out because they didn't have a method to find the distance. Right now, once this period luminosity relationship is established, then Edwin Hubble took the challenge and he tried to find the distance to this nebula, right? So what he has done was he had a telescope, which is a 100-inch one, and inside bracket I have 10 meters, 2.5 meters. And I am under the impression that you probably know what this means now, right? We have discussed about this. When I tell a 2.5 meter telescope, that means the primary, the diameter of the primary mirror, or if it is a refractor one, a lens, the diameter is 2.5 meters, right? So that is the idea. So normally we refer the 100-inch telescope or 1 meter telescope. That particular value means the diameter of the telescope. Right? And this telescope in Southern California at Mount Wilson, and this was actually world's largest telescope in 1920s. And as far as I remember, this telescope is still there in Southern California in the Mount Wilson. However, I guess it's just an exhibit now. As far as I remember, they don't use it anymore. And he photographed Andromeda Nebula, right? And he was able to detect several Cepheid stars within it. So he has detected several Cepheid variable stars. And once when you have the Cepheid variable stars, you can measure the distance, right? Now, Then he used the method that we have discussed before to measure the distance, and his measurements yielded and estimate the distance to this Andromeda Nebula is 1 million light years away. Right now, actually, modern distance estimates from modern estimates, we know that this is even further away. But this is, roughly accurate value at that time. And this demonstrates that the courtesy was correct. And if you go back to the debate that they have, it's the Sharkey argued that these nebulas were in our galaxy, but Kurtz argued that these nebulas were in a very distant galaxy. Now, after finding this period luminosity relationship and from the measurements made by the Edwin Hubble and applying this period luminosity relationship, he argued he found that this particular nebula is around 1 million. Sorry, what was that distance? 1 million light years away, right? So it clearly tells that this is a different nebula or different galaxy, which is what we now call as the Andromeda galaxy. So that is how this particular debate was scientifically resolved based on the measurements, right? Right. So that is the story about finding galaxies, which I want to. The take-home message from here is one thing is you need to know about this period luminosity relationship. That is very important. And at the same time, you can see that how scientists or astronomers think about finding something, right, that they don't know, right, using existing methods, right? So this is what you have to learn actually, or the skill that you need to build at the end, right? Now we know that at this point, we know that we have our own galaxy and there are other galaxies, right? So that's what I have mentioned here. Now we know that the universe contains billions of galaxies and Milky Way is just one of those. And each galaxy contains millions or billions of stars, right? So inside each galaxy, we have billions of stars, right? And we are just, you will see that when you look at these details, we have a very negligible position in the universe, right? And galaxies contains interstellar matter, stars, and apart from that, we have something called dark matter, right, which we have not discussed before. And these galaxies are normally held together by mutual gravitational attraction of its stars and other matter. You know that a galaxy is a one unit that collect there are stars and interstellar matter basically apart from the dark matter, and all these things are collected and kept as one unit from the gravitational attraction, right? Even the dark matter, right? Because they hold as a one unit, and that is actually the power of gravity. And galaxies are actually usually separate from each other by vast regions of mostly empty space. And so what that means is between two galaxies, there is a huge empty space between two galaxies, right? And because of that, galaxies are often called as island universes. So they are like little islands that contains their stars, interstellar matter, and dark matter, right? And held together by these gravitational forces. Right. Now, let's look at the details about the Milky Way first, because this is the galaxy that we are living. In 1785, an English astronomical William Herschel, so he tried to construct the first 3D map of the Milky Way, right? So to do that, what he needed is to find the distances to stars, because if you need to make a map of the Milky Way, you have to calculate the distances to all these stars, right? So that you can make a map. So he began by assuming that all the stars have the same intrinsic brightness. Right? So what he assumed is that he thought that okay, all these stars that we see will have the same brightness, right? Same intrinsic brightness or the absolute magnitude. Now, by measuring the apparent magnitude of each star, so he thought that all these have the same intrinsic brightness. So he measured the apparent magnitude of each star, and then he able to make a rough estimate of their distance, right? And from this work, he made a three-dimensional map of the Milky Way. And this is the map that he made, and which seems to be, not the map that we want, right? Because we know the shape of the Milky Way now, but this was the first attempt, and you can probably see that this yellow dot right here, close to the center of this map, is where he thought that our own sun and the solar system is located, right? And this is also not true, right? We now know that. Actually, the problem with his measurement is that he did not consider one important thing that now we know, which is very important in observational astronomy, right? So that is, so in his idea was that the Herschel's idea is that the Milky Way has a flattened disc-like shape. So he thought that Milky Way is like a disc, and his conclusion is that the sun lies at or near the center, as you saw in this map right here. And but this method has several issues. The most important one is that he did not realize how important is the extinction of starlight, right? Now this extinction, I guess I may have mentioned it in one of the lectures before. The extinction means when you look at these other stars from Earth, so the light from these stars has to travel through our galaxy and need to reach for us, right? Now what happens is the light, this starlight has to go through the interstellar matter, and then interstellar matter dims the starlight as it passes through, right? And when you have a star that is so far away, this effect is, huge or considerable compared to the stars that are nearby, because the stars that are far away has to go through this interstellar matter for a longer distance, right? Which means these stars will look like very dim for us. And this particular, and if you think about a very far away stars, they may be completely invisible, right? You may not even see those because their light is completely blocked by interstellar matter. And this particular effect has a very specific name, and that is called extinction, right? And this extinction is actually a huge issue in observational astronomy, especially if you are looking at stars that are outside our galaxy, right? When you look at other galaxies, because then they have to go through this interstellar matter, and this means that this tend to see same number of stars in any direction within the disk of the Milky Way. And this is why sun appeared to be at the center. And you can see what has happened to Herschel, right? He did not know about this extinction effect. And this is why he thought that all the stars, he normally see that the same number of stars in any direction, right? Because the stars that are far away, you can't see due to this extinction effect. Right. Now that was the first attempt to make a map of Milky Way. And then there was a second attempt to make a more realistic map of the Milky Way. And for the second attempt, So they have used an improved technique to estimate the distances again. And you can see that these distances measurements comes into play always. Right? It seems to be very important. Right? And the second method to measure distances came from a different type of variable stars. And those type of stars are called RR LIGA. Right? Now, remember that these specific names are given because they have very specific properties, right? All of them are variable stars, or we call them as pulsating stars. Now, these RR LIGA stars, they also vary their brightness regularly, and these are called pulsating. They are also pulsating horizontal branch stars, and this is related to this HR diagram, if you remember. And so these RR LIGA stars is also a kind of variable stars, which means these stars also change their luminosity or the brightness with the time. But there is an important property compared to the Cepheid variable. Cepheid variable had the periods between 1 to 50 days. But for these RR LIGA stars, their periods of variations are typically from half a day to a day in length. So which means they have a relatively short periods, right? So their period is kind of a very short compared to Cepheid variables. Now these are the important things that you have to remember and also get into your mind, right? So what are the important things about these different types of variable stars and how they are used to measure different things. Now, Cepheid variable stars used to measure the distances to other galaxies. So the first one was measuring the distance to the Andromeda galaxy. Now here we are using RR LIGA stars to make the map of the Milky Way, which means to find the distances within the stars in our Milky Way, right? So the other thing is all these RR LIGA stars have approximately the same intrinsic brightness. So their intrinsic brightness is roughly the same value. They are about 100 times more luminous than the sun. And because they have this fixed absolute magnitude, and they are probably the ideal for estimating distances because they have this fixed absolute magnitude, right? And here is a comparison between the Cepheid star variables and RR LIGA stars in one graph, and this these are Cepheid stars, and you can see that their period start around from 1 day and they goes up to 50 days, right? Their period is kind of higher, and these are the stars mainly responsible to find this period luminosity relationship and apply that to solve this debate between Shapley and Curtis to find that Andromeda is a different galaxy, right? And here are the RR LIGA stars, and as it is mentioned, you can see that their period is very short. All of them are less than 1 day, and they are roughly have the same luminosity, right? So that is why they are important, right? So in this class of variable, the time the star takes to go through a cycle of luminosity changes is related to the average luminosity of the star, right? So you can read the details about those. And these RR LIGA stars are used to make the second map, right? And one thing about these RR LIGA stars are they often found in globular clusters. And remember that we talked about open clusters and globular clusters. And these type of different stars like RR LIGAs are mostly found in globular clusters. Globular clusters are the older type of clusters, right? And in 1970, this astronomer called Shapley identified around This RR Lyra stars around in 93 globular clusters in our Milky Way, and this was very helpful to measure the distances to these clusters, because once you identify RR Lyra star from that previous graph, you can easily find the distance, right, from RR Lyra stars. And he has found RR Lyra stars in 93 globular clusters, and then found the distances to these globular clusters, right? And what he found was that these globular clusters were distributed roughly spherically throughout the Milky Way. And so from his measurements based on this RR Lyra stars, he estimates that the Milky Way is about 100,000 light years in diameter, and the sun was not at the center, right? And his estimate was that the sun was about 25,000 light years from the center of the Milky Way, right? Now we know that this is roughly correct, even though not exact. And here is the new map that he made for our own Milky Way, and you can see that this map makes sense compared to the previous one, right? Because you have these globular clusters, and you have measured the distances, and you can see that this map is more accurate compared to the previous one. Right now, if you look at from the details that we know up to now, if we look at the structure of our own Milky Way, the galaxy has three distinct components. There are three main components for our galaxy. The first one is called galactic disk, which is a large, flattened in shape with the built-in spiral pattern of the stars, right? And it has also interstellar matter. And there is the first thing, you have a disk with these spiral patterns of the stars. So that, indirectly tells you that there are a lot of stars in these spiral arms, right? And interstellar matter. And most of the Milky Way's young stars, star-forming regions, and interstellar matter are found here. You can see that all in these spiral arms is where you have a lot of young stars and star-forming regions and interstellar matter, right? And by the way, I can see you a nice example of this. See. So I'm going to show you something here. See if you can. I don't know whether you can see. So I hope that you can see the screen that I have shared. And by the way, just to explain you, this is one of the image of a galaxy cluster that I took from, I guess this is from 4-meter telescope in the Kitt National Observatory in Tucson, Arizona, USA. And the year that I took this one is maybe 6 years ago for one of my PhD theses. And what you can see, what I want to explain here is relating to these spiral shaped galaxies, which is our Milky Way is also a spiral galaxy. I can show you by enlarging this, zooming into this image. I don't know whether you can see, here is a spiral galaxy. So let me center it a bit. Right, so this is a spiral galaxy. Let me change the scale a little bit. So this one actually is a spiral galaxy. And so what I want to mention here is these are the spiral arms that you can see right now. These this galaxy cluster is around somewhere between 100 to 200,000 million light years away from us. And you can see that how powerful is this telescope, right? To take an image of a galaxy cluster which contains, thousands of galaxies in that. And inside that galaxy cluster image, you look at a galaxy, and this galaxy, you can even see the spiral arm structure, right? You can see that how powerful is these telescopes and the cameras. And what I want to tell here is this particular image is taken from using an H-alpha filter, as far as I remember. Now, H-alpha filter means you filter out all the other components of the light and looking at this H-alpha component, right? So the H-alpha is mainly responsible to show you regions where you have active star formation. Now, this happens due to the fact that when you have new stars, they emit a lot of ultraviolet radiation, which can excite the surrounding interstellar matter. And as a result of that, once you excite the surrounding interstellar matter, they emit H-alpha, right? So if you have a lot of H-alpha in a certain part of the galaxy, that means there are a lot of active star formation inside that, around that region, especially these new stars, like O and B type stars, right? Remember that O and B type means in terms of the spectral classes, right? So we have talked about that. So here is an example for that. Now this, you can see that most of the time, if you look at these spiral galaxies, let me see whether I can show you another one. Right here is a nice one right here. So take it in the center. You can see that this galaxy is clearly see that this is, let me show you this. Here is the spiral arms structure, right? Now you can clearly see this spiral arm structure when you take an image from H-alpha filter. That's because all the star forming regions are recorded in the H-alpha filter, and most of the time you should be able to see this nice spiral arm structure when you look at these large spiral galaxies through H-alpha filter, because most of the star forming regions are in these spiral arms, right? That's what I want to tell you, and let me go back to the presentation. Right. So that's what it means here, right here. You can see that most of the Milky Way's young stars, star forming regions and interstellar matter are found here. That is, those are the spiral arms that are located in the disk of the galaxy, right? And then you have the galactic bulge, which is relatively small and spherical in shape and lies at the center of the Milky Way. And I will show you a nice diagram of all these regions in the Milky Way. And this bulge is a dense region which contains many different types of stars and interstellar matter. And then you have the galactic halo. This is a very large and spherical in terms of its shape. And halo is normally made of relatively old stars and clusters, right? And this contains very little amount of interstellar matter. And that's why you have older stars, right? And this particular image kind of nicely explain all these three regions. What you have at the here is at the center is galactic center, and then you have this bulge from this light blue color, so that is galactic bulge, and then you have the disk, right? And disk is also divided into two parts: a thick disk and a thin disk, right here. Right? And these diagrams are actually very useful, even if there is a question for you to like describe, different parts of the galaxy or something like that. You can use a diagram like this, which to explain it, not just only the diagram, but you can have the diagram and explain it a little bit in terms of from your own words, which will be very helpful, right? And then you have this halo. You can see that the halo is very large. It extends to a certain, to a large distance outside the disk. And then the halo, you have a lot of older stars, and that's why you have a lot of globular clusters in this area. And also, most of the dark matter is also in this galactic halo. You will see that, right? Right. So if I go back to the center of the Milky Way, so what I'm doing here is just explaining different parts of the Milky Way that we have here, the center, and then you have the galactic uh, uh, halo, disk, and the bulge. So let's look at the center. The center of the Milky Way is very interesting. The central region of the Milky Way is the bulge is called the nucleus. So that is, so here is the central region, and this at the very central region of this bulge is what we called as the nucleus of the galaxy, right? And that region contains very high density of stars and looks very unusual at different wavelengths. And you will see why. It's very the center of the galaxy is very, very unusual, right? And even you cannot see this nucleus region from the optical light. So which means from normal telescopes, you cannot see it, right? And this is because you have a lot of dust around that. So the optical light is susceptible to this dust, so that you won't see anything. But if you look at the same from the infrared light, which is less susceptible to these extinction effects, which we have discussed before, his observation of stars close to the center of the nucleus indicate that they are orbiting at very high speeds. Right? If you look at the central region from this infrared light, you can see that the stars very close to the center of the nucleus are orbiting at very high speeds, unusually high speeds, right? And this tells you something, right, from your physics knowledge. What you can tell that if something is orbiting very high speed, what you can tell about the mass that you should have at the center. Anybody have an idea about that? And this is actually what you have learned in A-level physics, right? From this circular motion. I mean, if the speeds are very, very huge, unusually large, let's say you have a star that's moving around at very huge speeds, right? Then what happens is, at the center, you should have a huge mass in order to that to happen, right? To produce that facility, right? Think about this simple circular motion that you learned about in A-level physics, right? So this is where you apply those, right? Because actually what has happened here is there is a supermassive black hole at the center of our Milky Way, which is around 4.5 million solar mass. So it's a huge black hole, right? And you know that what black holes can do. We discussed about that very briefly, right? Black holes will be, they are the main source of, they have a huge gravity, so they can attract everything that are nearby. So this huge black hole is the one that is responsible for these huge speeds that you have for these stars, which are very close to the nucleus of the Milky Way, right? But you cannot see the black hole from an optical telescope. But what you can experience is these large rotational or high speed stars that are orbiting around the center. That's what astronomers have observed. And from this observation, by combining the physics knowledge that they have, they concluded that there should be a very huge, a massive object at the center of the Milky Way, right? And then later they have discovered that there is a supermassive black hole at the center. And you can see that you don't need things. Even from the very simple physics, you can get a lot of information, right? If you think it in the correct way. So that's the idea. Right? And of course, later from the radio observations indicated the presence of a very bright radio source known as Sagittarius A, right? And these observations indicate that the nucleus of the galaxy harbors a supermassive black hole with a mass of 4.5 million solar masses, right? So that's what you can see at the center. And right now, this is a schematic representation of our galaxy. And for the galaxies, when you observe a galaxy from a telescope, there can be two ways that you will see depending on the orientation of the galaxy, right? So if you see a galaxy in this way with all the spiral arms and everything, which is the same one that I just showed you from one of my own images that I took. If you see this spiral of structures and everything, that means you are looking at this galaxy. We call that as a face-on view, right? Which means you are looking at directly the face of the galaxy, which you can clearly identify all these spiral arms and everything, right? And then the other way that you may observe a galaxy is called as an edge-on galaxy, because galaxies do not orient in the way that we want, right? So when you observe the sky, they could be orienting different ways, but when you look at the galaxy, sometimes you may see a galaxy in this way, which is the most familiar way for us. And you can probably see that I have shown you a picture of one of these galaxies. You can clearly see the spiral arm. So that is a galaxy in a face-on view. But there are some other galaxies which looks like spiral galaxies, which looks like this. You just see the picture in this way, right? So what that means is actually you are looking at the galaxy in the edge-on view, which means you just see it from a side and just rotate this spiral galaxy in the face of 90 degrees, then you will not see all these spiral arms, right? Instead, you will see something like this, right? And this particular one view is called as the edge-on view, right? And these names will be important for you in one day, especially if you are doing a research in this area. They are frequently used words, so that's why I have mentioned it here. And all these white dots that you see, they are actually globular clusters, right? Globular clusters are kind of the clusters that contain all the stars, and because of that, most of the globular clusters are normally located in this halo of the galaxy. Right now, that's the constitution or the structure of our Milky Way, and this is pretty much common to all the other similar type of galaxies. And right, so I just have a question here asking, can I explain about the connection between galaxies? Sajini, I didn't completely understand what you mean by connection between galaxies.
Sir, I want to know if there's any connection. I mean, what effects if there's any connection between galaxies?
You mean whether two galaxies can collide with each other, or is it something like that?
Like that, yes.
Okay, so we will come into that. So I just keep that question. So you will get the answer in the next lecture, right? I will have a separate lecture about these mergers between galaxies and something called galactic cannibalism, which means there are events that two galaxies can collide, and sometimes there are times that one galaxy is get eaten by the other, which we call as the galactic cannibalism and those kind of things. So I will be briefly discussing about those in the next lecture, right? That is actually one of the interesting things that you can look at, what happens to galaxies when they collide, and it's one of the nice topics that we can discuss we will not have time to, discuss everything in one course, but I will briefly introduce it in next, probably not today, since we are, yes, not today, but I will talk about that on the next day. I have a separate lecture for you about galaxy properties and galaxy distribution of galaxies in the universe, which means I will talk about different types of, interactions between galaxies, and then also all galaxy clusters. Right. So thank you for that question. So I will discuss about that on the next day. And motion of the stars in the Milky Way. Now let's look at, now we know that the Milky Way has three distinct parts: disk, bulge, and halo. And we briefly discuss what you have in the bulge, especially about the central region of the bulb, which we called as the nucleus. And we know that we have a supermassive black hole at the center. And what is important there is how you detect those, right? So that's what I mean, as a fact, you can remember that there is a supermassive black hole at the center, but as science students who are actually doing advanced courses, what you need to know is to simply explain to someone how do you know, because I mean, everyone can read and tell that there is a supermassive black hole at the center, right? But if somebody asks from you, how do you know? There is very simple physics that you can explain it, right? Because of the stars that move around are very fast, you can first decide or conclude that there is a huge mass for that. Therefore, those unusual speeds of the stars. Right? I mean, you will see that in the next coming slides. I will show you one slide that astronomers actually have measured these speeds and the paths of these stars. Right. Right. Now let's look at how the stars inside this our own galaxy moves here and there. Right. What kind of motions that they have for the star. Now each component, which is this bulge and halo, have different mixtures of the stars and interstellar matter. In addition, they have different kinds of motions. Right now, if you take the halo and the bulge of bulge stars, so the stars that are located in the galactic halo and the bulge, so which means the bulge is this region right here, the blue region, and the halo is this large spherical shaped region. So if you look at the stars in this halo and bulge, the stars in those two regions are orbiting different random directions, right? They don't have any specific directions. They just go here and there. And they often pass through the disk, and you can see that the disk is, kind of at this in the flat space with this bulge and halo. So these stars in the halo and bulge, they pass through the disk and they move in random directions. There is no specific direction for those, right? And for the disk, on the other hand, you have the disk, so that the stars in the disk also orbit around the center of the galaxy, but the stars in this disk orbits in more orderly, which means they have a direction that all of them kind of revolve in the same plane. And what I have observed is stars close to the center move more quickly, right? So that's what I have mentioned before as well, right? When you go closer and closer to the center of the disk, which is again close to the nucleus, the stars normally move quickly compared to the stars in the outer region, right? Now the sun orbits at a speed of about 240 kilometers per second. And you can see that normally you probably have this idea that the sun is stable and we are moving around the sun, right? But the truth is, when you look at the big picture, compared to the Milky Way, from the center of the Milky Way, the sun is actually orbits around the center of the Milky Way at a speed of 240 kilometers per second, right? And you can see the speed here, even though we don't feel it, we are moving at the same speed, right? Because we are in the solar system now. And So this means the sun orbits the Milky Way every 240 million years. So it takes 240 million years to complete one orbit. Even though the speed is huge in our day-to-day compared to our day-to-day life, it still takes 240 million years because these are huge objects. Right, now here is a picture of the movement of these stars for the bulge, halo, and the disk, and you can see this orange and yellow arrows are the movement of stars in the halo and the bulge region. Then they do not have any specific direction, right? So they just go here and there. But if you look at the disk, there are stars that they move in an orderly manner towards the same direction, right, on the disk. So that is what I want to mention here. So make sure that what is important here is to understand and remember these differences between bulge, halo, and disk while you are looking at. Once you remember the differences, it automatically gives you the idea about the characteristics of these different parts of the Milky Way. Right? And this is just an optical image of the Milky Way at the center of our galaxy. And here is an image of the Sagittarius A, which is a radio image taken from VLA, or Very Large Array of Radio Telescope. And this is specifically looking at the center of the Milky Way. And this bright spot right here, in this lower right here, I guess you can see, if you need, I can just, this bright spot right here. This is called or named as Sagittarius A, which is the brightest spot towards the center. And here is another image, radio image of this galactic central region. And here is where you have the Sagittarius A, and this is the place where we think that we have the supermassive black hole at the center, right? And I have some more details here so that you can read through. Right, here is an near-infrared view of the galactic center, which are actually images the movement, track of the movement of the stars at different different stars, and astronomers actually have measured the speeds, and so these circles refer to their paths and different paths, right? So these are actually the inner the image is inner 1 arc second or 0.13 light years of the center of the galaxy, which is observed by the Keck telescope. And this Keck telescope is actually located in Keck Mountains in Hawaii, which is one of the islands in USA. So this is one of the, just for information, one of the best places to observe the sky, right? Which has a very, very nice sky, and it's a very high altitude mountain, and sky is very clear. So you normally used to get, and you have the best telescopes there, and you normally get a very clear view, and sky is very clear with less disturbances, so that you can observe and get nice images. And one of the key places for observational astronomy. And these circles that you see here is actually tracks of the orbiting stars measured from 1995 to 2014. So for a period of around 20 years, they have measured the tracks of these orbiting stars. Right? So what they have observed is these stars are moving around the center very fast, and their tracks are all consistent with the single massive gravitator. So when they have these tracks for their paths, the astronomers have found that from the data that there should be one single gravitator that resides in the very center of this image, and that is the effect of that supermassive black hole, right? Right, so let me, so there are a lot of details there which I cannot, I guess, finish now. So let me stop at this particular point for today. So I will explain you how to measure the mass of the Milky Way, and then a little bit more about some properties of the galaxies and about the dark matter next day. And then I will move on to the topic about distribution of galaxies, which we basically talk about clusters of galaxies and different interactions between galaxies, which is probably the answer for the question that Sajni raised. Right. So anybody else have any questions for anything up to now that we discussed?